important going on in science. And you have to understand this stuff, not just to study chemistry, though definitely to study chemistry, but even if what you really love, you find animals interesting and you want to study biology, you have to have an understanding of basic chemistry to study biology, right? You would say that's true? Yeah. So, has anyone ever been to the shop to see the tires get changed on the car? Right? Maybe, yeah. So maybe mom and dad want to put snow tires on, or maybe they just had to buy new tires. But they put them on, and so they'll take a rim and they seat the tire. You've seen that, right? And then they inflate it. And then they put it right on the car and you drive away? Is that true? No, what do they do? Does anyone know? Any gearheads out there? I know none of you have taken auto here yet. Yeah.
Hey,
not too bad.
Question for you.
Yeah.
Do you have an Ethernet Thunderbolt adapter?
I have an Ethernet USB adapter, which you're welcome to. Is that helpful to you at all?
That would be greatly helpful.
Okay, there you go.
Thank you very much.
Look at that. Man, I was able to like that. Okay, yeah, you definitely have to lift the car. You don't want to take the tires off without lifting it. That would be problematic. What else? Aha. They have to balance it because we put tires on our car and then we spin them really quickly, right? If the tire is unbalanced, what do you feel driving it? Yeah, that thing's going to shake, 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 and you feel it in the car. Has anyone ever had that experience?
Yes.
My wife, I hope she wouldn't mind my saying this, but it's true. My wife's a menace to society on the road. She might be the world's worst. Hi, Britt. She might be the world's worst driver. Now, the plus side is this. She has never been in a high-speed collision, ever. She's very safe. She's very safe on highways and roads. Parking lots.
Yeah.
My wife struggles in parking lots. I think she gets distracted. I think she sees where she's going and she's thinking about. She hits a lot of things in parking lots. Lots of curbs, occasionally other cars, the occasional pole. I wonder if I have that photo on here to show you. I will see if I can find a photo to show you. Anyway, she's had some parking lot adventures, shall we say? And I've at numerous times in my life gotten a phone call from a parking lot. Yes. What did I? Well, remind me what it was after, and if you remember to remind me, and we can figure out what it was, I'll show you.
Oh yeah, the video on that thing.
Oh, the blimp.
Yeah.
Oh, okay. Yeah, we will look at that because that's quite interesting, but not right now. So anyway, if after my wife has knocked into a curb good and hard, and there's a little bend on that rim, and now all of a sudden that wheel's out of balance, and you can see this by the way. If you go look at the rim of your car, probably, especially if you have mag wheels, if you have magnesium alloy wheels or aluminum alloy wheels, you'll see that there's little strips of weights that are put at various plates on it to balance it. Has anyone ever noticed that before? If you haven't, go look at the wheels of your car. And if you can see the inside, you'll see that they actually take little weights and they'll say 5 grams, 10 grams, 20 grams on it. And they just glue them to the inside of the rim at key points so that the wheel will be balanced. Because if not, when the wheel spins, it will shake. And if it were imbalanced enough, it could actually shake enough to cause damage. Does that make sense? In science, we often use something called a centrifuge, where if you have a liquid that you want to separate into parts, you put a test tube into a machine and it just spins it really quickly. And as it spins it really quickly, the heavy things go to the bottom and the light things come to the top. Well, if I only have one test tube that I want to spin, I have to make sure that I put a second test tube, even if I'm not actually interested in it, and fill it to the same level across from it, because the centrifuge has to be balanced. Does that make sense? And if it isn't balanced, a centrifuge spins fast enough. They spin 7,000 RPM, 7,000 rotations per minute, which is fast. If it's not balanced, it'll just fly apart. It would just break. Does that make sense? Okay. Electrons spin around atoms at the speed, almost the speed of light, very, very close to the speed of light, because they're very, very low weight. And the lower weight something is, the faster it can move. That's a universal truth. So, look here. You remember when we drew the Bohr-Rutherford diagrams, I said you always have to balance them north, south, east, and west, and we put them in pairs. That's because as these things rotate around the nucleus, they have to balance one another out. And if they don't, the atom wants to fly apart, just like the wheel on your car. Does that make sense? So for an atom to be stable, it needs its electron shells to be balanced. What's the other word we use for those shells, by the way? We call them shells, or? The valence is a specific one. The valence is the outermost one. Orbitals, good. So we need the shells or the orbitals. Those are two words that mean the same thing. To be balanced. And the easiest way, the most common way for them to be balanced is to be full. A full orbital is always a stable orbital. An orbital that isn't full likely isn't stable. It likely wants to fly apart because it's not balanced. And the result of this means that the atoms that we've had you carefully draw on your Bohr-Rutherford diagram sheet, like this, likely can't exist the way they do all by themselves in nature, because most of them don't have full shells. Well, some of the shells are full. Which shell is typically not full in an atom? Yeah, the valence shell, which is which one?
Most outer shell.
Yeah, the outermost shell is usually not full. So chemical reactions happen. We said that when things bump into each other, it's the electrons that bump into each other. Chemical reactions happen because atoms are trying to be more stable. Aren't we all? But they're trying to be more stable. And the way they do that is by trying to have full shells, full orbitals of electrons. Does that make sense? So I want to look at an example, and I want to draw a Bohr-Rutherford diagram for two things. And we're going to talk about sodium and chlorine. Sodium and chlorine. So I might need some help here. Sodium, what's its atomic number? 11. So what does that tell me about it? 11 protons. And then what's its mass? 23. So how many neutrons will it have? If it has 11 protons and a mass of 23, 12. How do we get that number? Yep. Very good. 23 minus 11 tells me it's got 12 neutrons. Now, here's what I want to do. If we can, based on yesterday, I want to try to draw this without actually counting up to, I mean, we know how many electrons it has. It must have 11. But let's not even do that. Let's look at its location on the periodic table. What row is it on the periodic table? What period? So that tells me what about this then? Very good. It's going to have 3 orbitals. So I'm going to go ahead and draw those 3 orbitals. Oh yeah, 1, 2, and actually I've gone too big, so I'm going to make that 3, and I'm going to draw a little mini orbital in here. I think I hate that. Yeah.
Can't you resize things?
I can. Okay. There we are. I'm doing my best, okay? Now, we know from the periodic table that the lower orbitals are always full, right? So this first orbital, how many electrons fit in there? 2. That's going to be full. And the second orbital is going to be full. And how many fit in there? How am I going to draw those, by the way? Very good. And whoever said pair them up, that's exactly right. And whoever said I did, way to take the credit. In a perfect world, I like to think it wasn't even you who sat in the first place. Okay, so there we go. Now, From the periodic table, which family is sodium in? Which group? It's in group 1. What does that tell me about sodium? It's unstable, but what else does it tell me? An alkali metal? Fantastic. Those were all good answers. The fact that it's in group 1 means that it's got 1 electron in its outer shell. Remember, we can always just count from the left to see how many electrons are in the outer shell, right? And sodium is just the first element. So it's got 1 electron in its outer shell. Yep. Cool. I want you to take 30 seconds and do the same thing for chlorine on the right. So that is sodium. I want you to take a minute and repeat that for chlorine. Give me a nice Bohr-Rutherford diagram for chlorine there.
Chlorine is CH, right?
Nope, chlorine is Cl.
You did it right. I did.
Wow, that's weak, but okay. Calculator? Yeah, you bet. You got it.
You're kidding.
Get drawn. Yep. I'd love to. It looks good. Very good.
Yeah, and then there was one more.
Yep, that's perfect. Okay. I hope I'm not rushing you, but I'm going to. What can you tell me about the nucleus of chlorine? What can you tell me about its nucleus? Yes, sir. Very good. So it's got 17 protons. How did he know that? He's right, of course. Yep, very good. It has an atomic number of 17. How many neutrons does it have? Have you figured this out? Does it necessarily have 17? How do we figure out the number of neutrons? What did you get? You got 18. How did you get 18? Shh, guys. Good. So we looked at the mass. The mass is 35. And we subtracted from that 17. And that gave us 18. So 18 neutrons. So remember that the protons plus the neutrons need to add up to the mass. Right? Does that ring a bell? Great. Perfect. Okay. Now, without even counting, based on the periodic table, I drew 3 shells. How do I know there were 3 shells? Beautiful. Now, what will I know is true about the first 2? Yeah, Connor. Good. The first 2 are full. So that's going to be how many in the first one? And how many in the second one? Good. Now, I know that we could count up, but just looking at the periodic table, can I tell how many electrons have to be in that third shell? What would I do? Yeah, now we have to be a little careful because this is group 17. Is this going to be 17 electrons in the outer? Now on yours, it probably says it's also 7A, right? But the fail-safe thing you can always do is what? We could do that, or we could count them. All right, and I'm a count on my fingers kind of guy. You know, a math teacher. So for me, I look over at chlorine and I say, how many over is that? 1, 2, 3, 4, 5, 6, 7. Does that make sense? I just count from the left. And that big empty space, do I count that? No, because it's a big empty space. I just count the elements. So again, I would say, okay, chlorine is there. It is 1, 2, 3, 4, 5, 6, 7 elements over from the left. That's going to tell me how many electrons are in that outer shell. Now, could I have just known that there's going to be 17 electrons and counted up? Yes, that works. Nothing wrong with that. But again, since we are learning how the periodic table is set up and why it's set up the way it is, there's no reason not to use it to give us quicker answers. Does that make sense? Okay, so I'm going to put 2 here, and 2 down here, and 2 up here. That's 2, 4, 6, and how many more do I need? 1. Now, that brings us to 17 electrons, which balances the 17 protons. That matches the periodic table. That's what chlorine looks like. That's what sodium looks like. Now we set above that a stable atom has to be a balanced atom. And the easiest way to be balanced is to have what kinds of shells? Full ones. Does sodium have? Sodium has 2 full shells, but then its valence shell is not full. There's 2 ways it could become full. What could we do to sodium to make its shell full? Give me one of them. Okay, but just in terms of just the picture here, if I wanted to make this a full shell, I could have only full shells. I could do 2 things. Which one of them? Yeah, in fact, I'd have to add 1, 2, 3, 4, 5, 6, 7. So I could give sodium 7 more electrons. Does that make sense? And now it would have a full shell. Or I could take away 1. Those are both, in theory, possible. Which one sounds practical? Good. In this case, sodium is going to have a much easier time losing 1 electron than finding 7 random electrons, which means that in nature is lazy. There's one thing we learn about science, it's that the universe is a lazy place. It does the easiest thing every time. That's an actual principle in science. It's called entropy. So sodium is going to want to lose that electron. Now let's look at chlorine. What does chlorine need to have a full stable order shell? There's 2 things it could do. What's one of the 2 things it could do? It could get 1 more electron, or it could lose. And how many would chlorine have to lose to have no partial shells? It would have to lose 7. So again, what is easier? Getting rid of 7 things or just adding 1 more? And I obviously picked this example for a reason, because the numbers work really nicely. What is something that could happen here really easily? They could go together. Sodium will do what? That's right. Sodium is going to take its electron and just get rid of it, give it away. So what would happen is these 2 things would bump into one another. And then, chlorine had been living kind of its not very stable atom life, feeling really out of balance and out of whack, and it's, freaking out all the time. And sodium's really imbalanced. They bump into one another. And then chlorine's like, whoa, do you have like an extra electron hanging around? That's crazy. I need 1 more electron. Because atoms talk. I don't know if anyone's ever told you that before. That's a little known thing. They speak. English, nonetheless. And it's in Spanish subtitles, just if you're wondering. Those are the 2 languages when they talk. It's the weirdest thing, but right at the atomic level, subtitles. Okay, so sodium will actually give its electron away. And we say that it
Oh no.
This is a mutually beneficial activity. Yeah. Sodium wants to have full shells, and it can do so by losing an electron. But electrons can't just float around nowhere. They have to be orbiting a nucleus for the most part. So it has to wait to find something that wants an electron. Chlorine comes around, and chlorine wants an electron. And the result looks like this. Now, sodium still has 11 protons and 12 neutrons, because does this reaction have anything to do with the nucleus? No. The nucleus is completely uninvolved. But now, after it's given up an electron, how many shells will sodium have? Yeah, so in this situation, where sodium would normally have 3 shells, after it's given an electron away, it only has 2. And the nice, wow, that was really pathetic. That's not much better.
Wow.
I'm doing my best. There we go. I'm not an art teacher. But I can find a USB network adapter like that. Bam. Okay, but how many electrons are in this first shell? 2. And how many are in this second shell?
8.
And Mr. Lonely Electron is gone. Because 1 is the loneliest number. Okay, now, here's what I want to note, though. We need to pay attention to something. Now, how many protons does this have? 11 protons. And what is the charge of that? It has an 11 charge. How many electrons now? 10 electrons, which is a negative 10 charge. What's the overall charge of this thing now? Ah, this now has a +1 charge. That makes sense, right? It's given away something that was negative. And this is something you should learn in life. If you get rid of things in your life that are negative, you become more positive. No, listen, I'm not even, thank you very much. Yeah, no, really. And the way we show that is we're actually going to draw a little square bracket around this, and we're just going to put up at the corner +1. This now has a charge of +1 because it gave away a negative thing. That's right. Sodium is ready. Sodium ready. And the way no, because its protons haven't changed. And that's a great question. The question is, does it become neon? And the answer is no, because the atom is always determined by how many protons it has. But in terms of its chemistry now, it's going to behave like neon, which is to say neon already has a full shell and is really stable. Now this thing has a full shell and is really stable. The only difference is, to make that happen, it had to take on a charge. And that matters. We're going to talk about that in a minute. But before we talk about that, I want to talk about our other friend in this. And our other friend in this is who? Chlorine. And chlorine, sorry, how many protons, how many neutrons? Is it 17 and 18? Cool. And how many shells does it have? It has 3. But what is now true about its 3 shells? They're all full. By the way, on the next page, I'm going to teach you a quicker kind of diagram to make. And you're going to thank me. But I'm also going to thank me, because drawing all these Bohr Rutherford diagrams is exhausting.
Well, why didn't you just tell us this before?
Because it's like anything else in life. You know, if you're born with $1 million, you don't appreciate what it's like to be a millionaire. But if you're born with no money and then got $1 million, you'd probably really appreciate that.
So you want to guess?
Do you know that the overwhelming majority of people who win the lottery end up going bankrupt? Which is pretty depressing.
They spend all their money on cars and stuff.
I know,
And then they quit their jobs, so they have no income.
Okay, so now let's talk about chlorine in all of this. So chlorine now has 1 more electron, right? Because it took an electron from sodium. So now chlorine still has how many protons? 17 protons. So how much charge is that? Yeah, so a 17 positive charge. Oh, that was going to be a number sign. There we go. But how many electrons does it have now? 18 electrons. And how much charge is that? Ah, So what is true over here? It has a -1 charge. Okay. And how do you suppose I'm going to show that up here? -1. Okay. Now, I wish I'd left a little more room, but that's okay. This is a case of the first time you teach a note, not planning it well. And next time I teach this course, I will put like another little line at the bottom so I know how much space I'm supposed to leave. Whoops, but that's okay. Here's what we want to know. If something has a positive charge and the other thing has a negative charge, what do we know about opposites? They attract. Good. So we're going to write this. Oh, gosh, there really is no room. We're going to write it up here next to table salt. Once.
What if we do have room?
Yeah, once. Okay, once is good. Once electrons have been gained or lost. So I'm going to say transferred. Because I didn't leave any room at the bottom, which I already feel guilty about. So don't like guilt me further. Once electrons have been transferred, the atoms have charges. One of them is positive and one is negative. All right, does that make sense? In this case, which one has the positive charge? Sodium. And which one has the negative charge? Okay. When they have an opposite charge, they're held together. It's actually a very strong way to hold things together. If you have one thing that has a positive charge and one thing that has a negative charge, they will stick to each other. When we do our electricity unit, we'll actually demonstrate this. We'll take, but you can demonstrate, you can go home. If you rub a balloon against your hair, it actually transfers electrons to it. And the balloon ends up with a bunch of electrons on it, which makes it have a negative charge. And your hair ends up missing a bunch of electrons, which gives it a positive charge. And then if you put the balloon against your head, what happens? It sticks. Because opposite charges attract. So the opposite charges hold them together. Oh yeah, I got to redesign this note big time. That's okay. This is how we learn, by making mistakes. And we would actually, the way we write this is we just say that this makes a new compound, NaCl. Because it's a sodium stuck to a chlorine. So we just call it NaCl. And if we gave it, and we would give it the name sodium. And the way we tell ourselves they're stuck together is instead of calling it sodium chlorine, we call it sodium chloride. You actually don't have to worry too much about the naming. The naming is a part of the grade 10 curriculum. I just mention it now because it's nice to know what to call these things. Does that make sense? So in grade 10, you'll have to know how to name them. But in grade 9, it's nice to have seen it, so I can call it something instead of just calling it NaCl all the time. It's sodium chloride. By the way, what is sodium chloride? Yeah, it's just table salt. And this is really interesting. Sodium metal, again, we said it's a metal that's in group 1, so it's really reactive. In fact, you drop it in a little bit of water, it explodes.
Wait, what is that? When you say this acts similar to
Once it's lost its electron. So the actual reaction where this happens is really violent. But after the reaction, it's really stable. You're eating something that used to be really dangerous, stuck to something else that used to be really dangerous. But once they react, totally stable, we put it on our French fries. So think about it. Sodium metal explodes on contact with water. Do not eat sodium metal. If somebody says, hey, I've got some sodium metal, would you like to sprinkle it on your French fries and eat them?
Yes.
When you eat the French fries, they will catch fire in your mouth. But don't worry, because after catching fire in your mouth, they will release hydrogen gas. So then you'll have a mouth that's on fire with hydrogen gas in there. And hydrogen gas plus fire equals boom. Okay.
Wow.
Do not put sodium on your fries. By the way, it's really funny because on food labels, sometimes they say like, oh, it contains this much sodium. They do not mean it contains that much sodium. They mean it contains that much sodium chloride, which is different because chlorine gas, if you haven't already, you will learn about in history class, was used in the First World War. You guys ever talked about this before?
Yeah.
Yeah, so they used to take big vats of this, release it, and put big fans behind it, and just blow chlorine gas across the other soldiers' trenches. Well, chlorine gas is also really reactive. In fact, when it touches water, it becomes hydrochloric acid. Now, the nice thing is the inside of your lungs is really nice and moist. So a soldier would breathe this in, and then inside their lungs, it becomes hydrochloric acid. If you can imagine a more awful way to die, I can't. Where the inside of your lungs suddenly become covered with hydrochloric acid, horrific. Truly, truly, truly horrific. So if anyone offers you chlorine to sprinkle on your French fries,
Oh, yes.
also say no.
Honestly,
No.
if anyone offers you anything other than salt and pepper to put on
Also,
your
if strange people offer you anything to put on your fries, just say no. Yes. Sorry? That's interesting. In the water, the reaction itself doesn't need oxygen in the air. That's not what it's reacting with. It's reacting with the water, so you're not going to put it out. Now, if you were talking on an industrial scale, the answer is get it away from water. So you would want to spray something oil-based over it. So if you were trying to contain it on a big scale, you actually need to cover it with something it can't react with, and it can't react with oily substances. So if you look back there, we have some in the lab, and it's kept in mineral oil. It's kept basically in baby oil. Because there, any water you did put on it would float to the top. Because mineral oil is oily, but it's also heavier than water. So normally if you mix like vegetable oil and water, the oil floats. With mineral oil, if you mix it with water, the water floats. So it keeps the sodium safe from it. But yeah, so that's how we put out. But now here's the key. You take sodium, which is crazy and reactive, and you mix it with chlorine, and they will react. In fact, when you put sodium and chlorine together, this process, this transfer of electrons, is not like a peaceful thing. It releases tons of heat. Tons of heat. In fact, we would experience this, and we say, oh, that was a reaction that like exploded. It put tons of heat out. Yep. It depends on how much of the stuff you put in. Does that make sense? But if I took mass is always conserved. So if I took 10 grams of sodium and 10 grams of chlorine, it wouldn't actually work perfectly because the ratios matter. But if I took, let's look at the weights. If I took 20 grams of sodium and 30 grams of chlorine, I'd get 50 grams of salt. Because it just adds together. You're not destroying anything, you're not making anything, you're just sticking them together. Does that make sense?
So how do they safely make salt?
So these are all reactions that thankfully, because they're so reactive, we don't find just sodium in nature. In fact, we have to make just sodium. All the sodium in nature has reacted to become something else because it's really reactive. We don't find chlorine gas in nature because it's so reactive. In nature, all the chlorine gas has reacted. So it's not that we make salt in nature. The salt's already there. These reactions happened billions of years ago. But we as scientists can take sodium chloride, and with a bit of work in the lab, we can turn it into solid sodium and chlorine gas. So it's not that we have to make the stable thing, we have to make the unstable thing. And then we have to store them carefully so they don't go back to this, because they want to be stable. They want to react to form like this.
Salt people's cells work? Like, what do they have to do?
It's old dried out salt water from the ocean. Most salt is mined. So those, yep. We'll talk about dangerous stuff. It is chlorine, and it's dangerous stuff. Okay, so, sodium is the one that's dangerous to mix with water. Yep. When we put the chlorine in the water, it does make acid, and we put a little bit of acid in our pools to kill bacteria. But we don't want to put too much because then it would hurt us. Okay, so, I want to try this again. This time we're going to do it with lithium and oxygen. But first I want to show you something, which is, and we're actually not going to draw one of both. I'm getting exhausted of doing this. But let's talk about lithium. Okay. If I wanted to draw a Bohr-Rutherford diagram of lithium, what would I do? Lithium. What's going to have to be in there? How many protons? 3 protons. How many neutrons? I don't think so.
No, 4.
4. Why is it 4?
Because you got to round.
Yeah. Lithium's mass is 6.9. 6.9 rounds to 7. And 7 minus 3 is 4. Okay.
Wait, 3.
Now, let's look at its location. How many shells does lithium have? 2 shells. Okay. How many electrons fit in the first shell?
2.
And the second shell, how many will lithium have?
You put 2 pieces. Yeah.
Oh, look at me. I corrected Orlando's mistake in the snarkiest way I could think of. How many electrons in its outer shell?
I didn't correct it.
Well, no, let's take a look. What family is it in? It's in the first family, right? So it's going to have 1 electron. Okay, I want to teach you a new way to draw a diagram. A Bohr-Rutherford diagram is a great way to see how an atom works, but we said chemistry is all about what shell? The valence shell. So if I was going to do a reaction with like cesium, which is in the 1, 2, 3, 4, 5, the 6th period, do I want to draw 6 shells when the only important one is the outer shell? No. So we have invented something new. A guy named Lewis came up with the Lewis diagram. And a Lewis diagram looks like this. We draw just the valence shell, and the electrons are just dots. So it's sometimes called a Lewis dot diagram. So
we have the muffin diagram.
So if this is lithium, what in the heck? Well, that was weird. I don't know. But I know I blame, I don't know. So if that's lithium's Bohr-Rutherford diagram, here's how we do a Lewis diagram. And Lewis diagrams are a lot nicer. First, we put the atom's symbol. So what's the symbol for lithium? Li. And then we draw just its valence. And for lithium, how many electrons in its valence shell? Just 1. And we don't even put an E, we just put a nice dot. Isn't that much better? So that is a Lewis diagram of lithium. Now, I still want to follow the same rules about north, south, east, and west. Okay? So we still want to put them up, down, left, right, and make them in pairs. But other than that, we just draw it with a dot. I'm sorry for erasing and redrawing mine, but it occurred to me that on the first Lewis diagram I ever drew for you, I did a really lazy, careless one and just put the dot like in the corner. But we still put the dots like that. So let's talk about oxygen. What would oxygen's Lewis diagram look like? Well, first thing I have to draw is the symbol, which in this case is O for oxygen. Now, how many shells does oxygen have? 2. How many do we have to worry about here? Just the outer one. How many electrons in oxygen's outer shell? What should I do? The answer is 6. What should I do to figure that out? I'm not going to die. I mean, eventually I'm going to die. We're all going to die. But I'm not going to die right now. And that seems like a fairly rude thing to say to somebody. Yes? Yeah, good. So I'm just going to count over. 1, 2, 3, 4, 5, 6. And how am I going to put them? 1, 2, 3, 4, and now I've got to double up, right? So I'm going to double the right side and the top side, let's say. There we go. Can we agree that that's a little bit easier?
Yeah, wait, just a little bit.
Yeah. In practice, chemists never draw Bohr-Rutherford diagrams because they're a lot of work. But you actually draw Lewis diagrams quite a bit. It's often helpful to draw these to figure out what's happening. Does that make sense? So now, let's talk about how these would actually react. Let's talk about making an ionic compound. So let's go down below. We'll redraw this. If I have lithium and oxygen, and lithium has 1 electron. How many does oxygen have again? 6 electrons. Yeah, good practice for you. So there we go. Again, it doesn't actually matter where you put the 2 empty spots. Why do you think I've put my empty spots on the left side? Just what do you think? Why did I make my diagram that way? Because I'm going to do something between these two, right? Okay, now, this tells us really quickly, does lithium have a full outer shell? No, in fact, how many electrons are in its outer shell? What is it going to try to do with that 1 electron? It's going to get rid of it, and it's going to get rid of it by giving it to oxygen, all right? Electrons are like cats. It's not okay to just get rid of them. You have to give them to somebody. Okay?
Unless you're an evil person.
It doesn't matter how much you don't want to own a cat. You shouldn't just open your door and kick it out. All right? You got to give it to someone. That's like electrons. Now, once I have done this, is this lithium happy? The lithium. He's stable now, right? He's going to be no single electron making him unstable. Great. So I'm done. I'm done. I think I'm done. I said I'm done. I'm the teacher. I'm the teacher. Why don't I get to say when we're done? Okay, what do we think? Somebody has a hand up, so we'll go to him. Yeah, you bet. Okay. Shh. So what are you thinking? What's my problem? Oxygen. Is oxygen closer to being stable?
Yes.
Great. But is it all the way there?
No.
So should lithium just give it another electron? No, because then lithium wouldn't be stable. So what do I need? Another element. Now I could get a different element, but I've said that this is a reaction between what and what?
2 lithium.
Good. This is a reaction between lithium and oxygen. So the only other element I'm going to get is another lithium. Does that make sense? So, hey, there we are. So I'm going to have lithium bring a friend. Lithium's friend also has an electron. Unstable people need friends too. Trust me. Speaking from experience, when you're unstable, that's when you need friends even more. Okay, so what is this lithium going to do? Good. Lithium is also going to give away an electron. I did not line those up nicely, but that's okay. Does that make sense? And if we look at what we're left with, I'm going to draw an arrow to show that when we start like this, we end up with this on the right. I end up with lithium, and its valence is now empty. Could I choose to draw the orbital below? I could. I'm not gonna, because I want to show this is lithium that has given away its 1 electron. Hey, what is going to be true about lithium now? It gave away an electron. So what must be true about it now? I saw a hand. Trust yourself. Good. It's going to have a positive 1 charge because it gave away an electron. And electrons are negative. And when you get rid of negative things in your life, you become more positive. And let's keep in mind that there are 2 of these lithiums hanging around. And they both have a +1 charge because they both gave away an electron. What is next to them? What does oxygen mean? It's just...
-2.
It is -2. And why is it -2? Yeah, it received 2 electrons. By the way, I want to mention something. You will sometimes see me write -2, and you will sometimes see me write 2 negative. It's this weird thing where they're both acceptable. I try to, as a matter of habit, put the negative sign, then the number, but I will be a little inconsistent. I apologize for that. They are both acceptable. I don't know why. Now then, to make this work, we could say this has a formula of what? How many lithiums does it take? It takes 2 of them. So I'm going to say Li, and then I'm going to say how many of them it takes. And it takes 2 of them. And then what's the rest of it? Oxygen. And I could put a 1 here, but we do this thing in chemistry where if the number is 1, we don't write it because we're lazy. Our default is 1. So if we don't put a number there, we know that the number is 1, which, by the way, makes sense. For example, I would not tell you that, like, I drove 1 car to work today, right? That'd be weird. I'd just say I drove my car to work. On the other hand, if I drove 2 cars to work today, that'd be worth mentioning, right? So the number's there. Yeah. It is, for the purpose of grade 9, I'd be fine with it. By the time you get to 10 and 11, that was a great question. Would I say that you are wrong if you said Li2O1? In grade 9, I would not say that you're wrong. I'd be fine with that. By grade 10, because in grade 10 we have to know the formal rules, I would then say, it should be just 1. So I'm going to write it the way it is, but if the 1 helps you for now, go ahead and do it. That's okay. Now, again, you don't have to know this. You won't be tested on this, but you're clever people, so I bet you can figure it out. What would the name of this be?
Leo.
Lithium. Yeah, and then the other one's weird. To make it not sound, oxide would be consistent, but would sound goofy. So they just say oxide. Lithium oxide.
Oxidized.
Lithium oxide. Okay, your homework today is an easy one.
Stop giving us homework.
Stop giving you it. Listen, hear me out. If you don't like homework, don't take academic classes. It's a real simple solution. For the record, you should take academic classes. It's worth it. But yeah, you take academic classes, you're going to get homework. That's just the way it goes. And listen, I sincerely doubt you're doing as much homework as I am. Sure, I'm a teacher, yeah. Listen, do you think the average accountant goes home after work and does 3 hours of accounting a night? No. No, they don't. So, what I want you to do is for the first 20 atoms, I want you to make Lewis diagrams. Lewis diagrams are nice and easy, right? You're just putting dots. But I want them to be neat. I want them to be neat. And then for, you've got some time for Tuesday. So I want this to be done tomorrow. This is due tomorrow. And the supply teacher is going to check it. All right? That's okay. So this page, Lewis diagrams, that's due tomorrow. I want you to draw a Lewis diagram for each of these. So for example, hydrogen, I'll do the first one with you. We draw letter H, and what do I need to put here? 1 what? 1 dot, because hydrogen has 1 electron. And you could put it on any side. I'm going to put it B side up there. That's hydrogen. Is this going to take you long? No, it's not. But then, sorry, for Monday, not Tuesday, we're back Monday. For Monday, I want you to do this page. And I want you to do these just like the second page of this note. You'll note that it's periodic table shaped.
Yeah, why did you put the gap in?
Yeah, there's 2 gaps.
Who cares?
Oh, no, did I screw up?
Yeah.
Oh, sorry about that.
There's no gap.
Oh, you need a whole extra row. You're going to have to draw that in yourselves. Oh, I screwed up. Oh,
Leave it like this.
no. That's why.
We messed up.
Oh, wait, what?
Wait, I don't have a problem. Why can't we just leave it like this?
Well, you can. You just have to like get rid of that. Like, show me that that's. Oh, sorry about that, guys. Well, but it's not right there, right? Like, so in other words, right? Like,
Can we just write this goes down one?
you need to make a match that. I screwed up, which is all on me. Actually, you know what you could do? You know what you could do?
Just leave it as is.
I'm so confused.
Listen. Look, do me a favor. Shh. Look at the periodic table. Look at the periodic table. Then look at this, and you'll see that I done screwed up, but that's okay. We're just going to say gap goes here. And that fixes it, right? Okay, that's the easiest fix.
Okay, now we don't have to change anything else.
So yeah, instead of getting messy, we'll just say that there's a gap that goes right there. Sorry about that. Actually, sorry, it goes here, doesn't it?
Yeah, and that, I was like, what?
I'm just leaving it.
Don't just leave it. That's wrong.
I wrote gap goes here. It's general area.
Let me guess, you did it in pen?
Yeah.
Yes.
Oh.
Guys, listen, don't work in pen. We make mistakes in life, which means that we use pencil.
You're destined to make more mistakes with the pen. than you
Oh, I see what you're saying.
Yeah, it should go there. Okay,
And then, wait.
that's all. That takes care of it. That's all you have to do. You just have to say, hey, there should be a gap there.
Some of them want to say this about this part.
Because I was trying to be more complicated than I need to be. The easiest thing is just to put a gap there. Right? That solves it.
And then we fill
The first 20. That's right. We still have time? We good to go? Okay, it'll be the first thing you do tomorrow. Okay?
Oh, yeah, sure.
Oh yeah, I will.